Hello. Do you see my desktop? Does the
Yes.
desktop show up? Can you hear me? See a desktop?
Yes, I can hear you.
Okay, great. Yeah, I keep getting a weird interface. Every time I run Zoom, it acts differently. So I'm really sometimes unsure what's going on. Okay, let me get the chat up. Okay, what we're gonna do is do some more review of stuff on ML. Okay. Um, there's a reading assignment to finish chapter 7. We'll start talking about chapter 7 today about patterns. But first, I thought we'd look at a few more examples of what we were doing about types in ML. Okay, so here's the example we were working with in class yesterday, the day before yesterday, and I added some more examples in here of of of, of different ways you can declare types in ML. So, like, let's go through this list real quick. This function here, there's no type declaration anywhere in here. Okay, so ML has to figure out everything. So we want to practice thinking about types. Okay, now some of these have type declarations in them. See, that's a type declaration. That's a type declaration. There's another type declaration. There's another one. This one's not a declaration. Remember, that one's a function. So there's no colon, and that's in front of the variable. That's the function that takes an int and turns it into a real. Okay, so I've got a mixture of declarations and functions, and want to see how they affect the function I'm defining. Okay, and then there's some these all have two inputs. This is more or less the same thing, but with only one input. No, I'm sorry. Um, two. Yeah, actually, these are just more variations on these up here. Okay, then these have only one input. Same idea, but with one input instead of two inputs. Okay, so what does ML do when it sees that? Well, it says that there's an X and a Y, and you're taking their product. This operator can either work with a pair of X's, a pair of ints, or a pair of reals. Since you didn't say otherwise, it defaults to a pair of ints. So X is an int and Y is an int. Okay. Now let's look at this one here. This one says that there's two inputs. ML doesn't know what they are. Then it says, oh, something is a real. What's a real is the result of this expression. So it's saying that after you multiply X and Y, you should have a real. Well, the multiplication operator, there's two versions of it. One takes in two reals and gives you a real. One takes in two ints and gives you an int. Since you're saying that the result should be a real, that's what, see, the type, notice that this is something that Java doesn't let you do. I'm putting the type on a result, not on a parameter. Okay, this is one I want to point out that ML, the textbook points this out. ML lets you put types on results, not just on inputs to functions, but on the output. Well, actually, Java does. Java does let you do that, but when you declare a function, you say what the return type is. But notice that this is not the return type of the function. That would be done on the left-hand side. This is the return type of this expression. Okay. Okay, in another example, we'll see how to declare the return type of this function. Instead, we're saying that the return type of this expression is real. Well, but then ML says that that must mean that this is the product of two reals. So now this is a real and this is a real. Okay. Okay. Now over here, okay, let's skip 3 and go to 4. Here you're saying that this variable is a real. Now that's almost, but not quite the same thing as saying that this parameter is a real. Notice that the declaration is over here, not over here. Now that's something Java wouldn't let you do. Okay, see here, instead of saying that X is a real, I'm saying that X is a real over here in the expression part. Well, it ends up meaning, see, I could say it's here, I could put X is real here, or I could say X is real here. From the point of view of ML, it's pretty much the same thing. It's not 100% the same thing, but at least in a simple example like this, it is. That's a real. So that means this must be the product of two reals. So this one's a real also. So now both these are reals. Same thing here. This is a real. You go over here. That's a real number. Product has to be either two ints or two reals. This one is a real, so this one must be a real. So that one's a real. Okay. Now, we skipped this one. I actually don't know for sure what this one is doing. It could either be synonymous with saying that Y is a real, or it could be saying that the product is a real. I don't know the order of operations here. I actually wasn't able to figure it out by reading the ML documentation. It ends up having the effect of, these are all the same function. Well, these are all the same function, but I'm actually not quite sure what's the order of operations here? Is this bound to just the Y, or is it bound, or is the product done first, and then this is bound to the result of the product, which would be grouping it like this, okay? Or is it grouping it like this? I actually don't know. If it's grouping it like this and it acts like this one, it's saying that that variable is a real. It ends up having the same effect, but I actually do not know if this guy is bound to the variable, which means that it would have higher order of operation than this. This would be done first. You would bind the real to Y first and then take the product. Or it could be that this has higher order of operation. You do this first, and then the result is bound to real, which is what this one does here. It says do the product first, and then you declare that the result of the product must be a real. Okay. Notice the order of operations is tricky. Sometimes, this is an operator. It's essentially what Java, you might call the type of operator. And this is an operator. And I actually don't know which one's being done first. Is this the type of Y, which means that that would be done first? Or is it the type of the product, meaning the product would be done first? The moral is use parentheses. Yeah, the moral is this one, as far as I know, it's either this or it's this, and I don't know which one it is. If you're not sure, you should put parentheses. The fact that I actually don't know which one it is means I shouldn't really be using in the real world. I wouldn't use this if I really wasn't sure why it was doing what it was doing. If I want it to be that, I should say group it that way. If I want it to be that, I should say group it that way. So actually, I don't know whether this one is this one or that one, but they actually have the same effect. I couldn't figure out a way to make them have different effects. So I could not actually figure out which one this guy is. Is it this one or is it that one? Okay, order of operations can be tricky. So, and the standard answer to solve tricky problems with order of operation is use parentheses. Don't rely on what you think is happening. Be explicit. Okay. All right. Now, so this one explicitly said that X is real, which is the same thing as saying that X is real. Stylistically, I don't know which one ML programmers prefer. Would they prefer you write it this way? Probably write it this way rather than writing it this way. Okay, but ML, right? These are just experiments to show you all the different things that ML lets you do. What are the kinds of things the language lets you do? So you can say anywhere there's a variable, you can say what its type is. Anywhere a variable is put in an expression, if you want, you can specify the type. Now, if you do something dumb, like give a variable more than one type, you'll just get a compiler error. Okay, so you don't want to do dumb things like say it's an int here and say it's a real here. They'll just give you a compiler error. Okay, so but the thing is, you can put your type specification anywhere, like in Java where you're declaring the function, or you can scatter the type declarations where you want. In the real world of ML programming, what people do is they try to make their code as readable as possible. If this one makes it somehow more readable, then that's what they'll do. If they think it's better to put the type declaration in the middle of the expression, if someone thinks that makes it clearer, then they'll use it that way. If they think it's clearer to put the type over here, they'll do it that way. And if they think it's clearer to let ML figure out the types, they can just let ML figure out the types also. Remember, you don't, but anyway, if you let ML figure out the types, in this case, it was int. All these others are doing reals, except this one. Now this one's this one ends up being a little bit different. Okay, ML doesn't know what X is, and ML doesn't know what Y is. All right. Then it gets over here and it says, but X is the input to the real function. So that means I'll go over here and annotate it. That means X is int. Okay, because X is the input to the real function. The output of the real function is a real number. So the left side of the product has a real number. So that means the right side of the product must be a real number also. So now we know that Y is a real. That's interesting. We got a mixture. X must be int and Y must be real. Okay, because that forced X to be an int, the output of that expression is real. Real times must be real. So I got int real. Okay, notice that that's not obvious. Okay, now this would be an example where an ML programmer might say, you probably should have annotated that over here rather than let people try to figure that out. Like, instead of forcing readers to think like a compiler, it might have been nice just to say, well, I really want this to be an int and real. Okay, I think that would probably be better style in this case, because otherwise you're daring your reader to think like a compiler. Yeah. And that's usually not a good idea. It's not usually a good idea to leave it up to the reader to figure everything out like the compiler would. Okay. Now the next one switches it around. ML doesn't know what these guys are, doesn't know what X is, so doesn't know what this guy should be doing yet. Goes over here and says, oh wait, Y is the input to the real function. The real function takes in an int, so Y must be an int. So now ML can say that's an int. Okay, but the output of real is a real number. So real number times X means that X is now, we know, a real number. Okay, so thinking like the compiler, we know that this one goes X real, Y int. The other one was X int, Y real. Okay. All right. So those are kind of, that's thinking, that just learning to think like ML does. These are simple enough that most ML programs would leave them just like that. Yeah, because these are really simple. So it doesn't take a lot of work to figure out that that one was int real and this one was real int. But if the formulas start getting more complicated, it's probably a good idea to specify what you did want over here, rather than leave it up to the reader to figure out what the compiler is going to specify. Okay. All right. Now here's some more examples. This funny notation here, this is how I say the return type. Remember over here I said that I could specify either, like this was specifying the return, this specified the return type of the expression, which was the return type of this function, but it's not, for example, if I put a Z here, then I put Z plus, okay. Well, what's Z now? Well, this is the return type of that expression. So that expression returns a real. So that means this is the sum of a real with a real. So this guy's a real, and then you're adding up reals, so the return type of the function is real. But this was not the return type of the function. This was the return type of only that sub-expression. But then it turned into the return type of the function, okay? Down here is how I specify the return type of a function, and it's really weird. You put parentheses around the last parameter and put the colon after the parentheses. Without those parentheses, well, this won't compile. And this is the type of the parameter. Okay, that's the type of the parameter. That won't compile because of the order of operations being wrong. You put parentheses around the last parameter. You put parentheses around the last parameter, put a colon, the return type of the function. Okay. So that's the return type of the function. This is the type of the parameter. And let's see. Oh, well, you didn't need parentheses here. Oh, because it's at the end. Yeah, if it's over here, I need parentheses around the colon real. See, on this one, I need parentheses, but yeah, on this one, I actually don't need the parentheses. In this one, because it's the last parameter, I can get away with saying colon real, but I got to realize that's not the return type of the function. That's bound to the y. That's the return type of, that's the type of the input y. Okay. Every language has its own quirks to its syntax. It's not as if Java was the clearest language in the world. You're more used to Java, so you're going to compare everything to Java, and you're going to think, oh, that's really weird. If you'd have learned this language first, this would be second nature to you, and you might even think Java was kind of weird. It's important for programmers to learn multiple languages to force them to realize that not everything in the world is done one way. This stuff does make sense. You can get used to it, but you have to practice the language. And as I've said before, the ML way of doing things is becoming more and more popular. In the world at large, ML is having its influence on so many other languages. So this way of thinking of programming is not going to go away. It's probably just going to spread more and more. So it's a good thing to learn this way of thinking, this ML way of thinking. All right. So now I could specify the return type of the function, the type of that parameter, or the type of that parameter. Oh, here I declare everything. The type of that parameter is real, the type of that parameter is real, and the return type of the function is real. Okay. Now, here's one that's different. I'm saying that x is an int and y is an int, but the return type of the function is real. You go over here and you start looking. Well, does this make sense? This is the product of two numbers. They're either both ints or both doubles. Okay. I said they're both ints. So, okay. If I deleted that int and that int, they would default to int anyway. Okay. So I'd actually, that int and that int are redundant because this product would default to two ints. Now, the product of two ints is an int. But then this function takes in an int and returns a real, which agrees with this one here. Okay, so it takes in an int and it takes in an int and it returns a real. All of these declarations over here are redundant. They agree with what's over here, and I actually don't need them, but they might be nice to put them there to help people read my code. If someone read this, they may not realize that I meant int, return a real. Okay. Well, actually, obviously it returns a real, but they might think, well, yeah. And if you think a little bit about it, real takes in an int. So this thing has to give me an int. So that means this has to be the product of ints. So ML can go back and figure out all that if it wanted to. Okay. So here, I didn't really need this. So I dropped it here. I really didn't need this. So I dropped it here. So here I'm just kind of showing you that a lot of this type was redundant. In fact, I should have put one more in there. In fact, I didn't need that either. Okay. Yeah, that declares, all of those declare the same thing. This one has maximal type information in the declaration of the function. And this has no type information in the declaration of function. They give you the same thing. Okay, practice in reading. Okay, now here's one. X is an int, Y is a real, and I want the result to be an int. Okay, so I'm saying that X should be int, Y should be real, and the answer should be int. Okay, now let's look over here, make sure that does that. Product neither needs two ints or two reals. Okay, well, I said that Y is a real. Okay, that agrees. Okay, now this output is this is the output of the real function, so it's a real. So this is the product of two reals. But the input to the real function should be an int. And yes, I did say that x is an int. Now, the result of this is a real. The real going into the round function rounds it to an int, so the final answer is an int, like I said here. Okay, so everything I said here agrees with everything I said over here. All this type information was really redundant. ML didn't need it. Okay, but it could be figured out from over here, but it might be nice to let a programmer know it. Okay. Okay. And then notice that this information didn't. There's more than one way to get this signature. Int, real, int, x is int, y is real, output int. Here's another way to get the same thing. Okay. Here's a product. Product needs to be two ints or two reals. This guy is an int. Okay. So that's the product of an int. Okay. Now the product of an int needs an int on the right-hand side, but the product of ints is going to return int. Now this guy needs to be an int. Well, round takes in a real and gives me back an int. So this needs to be a real. And yes, this one's a real. So here's two different functions that give me the same signature. We call this the signature. The signature is int, real, int. In Java world, there would be the return type is int. This parameter is an int, this parameter is a real, and that parameter is an int. In Java world, that would be, let's see, this is F6G. In Java world, it returns an int, and it has int x and Java world would be double y. Okay, so that's the signature in Java. That's the signature in Java that agrees with this signature. Return type goes before the function name. Here, return type is weird, I think weirdly put after the last parameter. Okay. The input types come after a colon. Here, the type comes before the variable. Here, the type comes after the variable after a colon. Here, the type comes before the variable after a space. We put commas between parameters. Type comes before the variable. I think using the word real is way better than using the word double. It's just a bizarre anachronism that we use the word double to mean this. And remember, it was double because originally it was float, which is still a bad name. Float means floating point, scientific notation. It's actually, it's scientific notation. Scientific notation. Oh, I still didn't spell it right. I can't even barely see today. Scientific notation is often called, and that's what, when they invented this stuff back in the 60s, it was mostly used to do numeric calculations. Scientific notation was thought of as a floating point. And but that was 8 decimal places. At some point, they realized that, as computers got more and more sophisticated, they were able to double it from 8 to 16 decimal places. So some idiot said, let's change float to double. That was not a stroke of genius. You literally just doubled the number of decimal places in the floating point number, so somebody called the type double. It's too bad they didn't think to call it real, because those are real numbers. That's what mathematics calls them, real numbers. So in a math class, they're called real numbers, as opposed to the integers. So this is the name that's been used in and even float was a little bit better than double. But they couldn't call this float because float meant 8 decimal places. So they had to come up with a different name for 16 decimal places. And some people proposed this. I don't think anybody liked that, but that was actually an idea, float. That Microsoft actually eventually came up with something like that. They used it. float, you know, two floats. Nobody liked that. Somebody said double, and then good luck trying to explain to people why you call decimal numbers double. Like another name would have been fine, would have been decimal. It's a decimal number. That's probably the name that most people would have maybe chosen for it. Okay. Real is the number mathematicians do use for this. They're called real numbers. Floating point numbers or scientific notation is pretty common name in physics. Double is just dumb. You doubled the number of digits in a float, so you get double. Okay. Uh, uh, does anybody heard the expression, what's the two hardest problems in computer science? There's a joke. There's the two hardest problems in computer science are cache coherency and naming things. Giving names to things is literally considered by a lot of people to be one of the hardest things in computer science. Coming up with good names is considered really important and kind of hard. And you're stuck with the bad names you choose, like double. You get stuck forever with bad names. This is why it's hard, because if you don't come up with a good name, you can't like fix it later on, because you can't go back and change the C language and say, oh, we're going to call double real. It just doesn't work that way. You can't invalidate millions of lines of code. Once you've chosen a name, you're usually stuck with it. So the old joke is the two hardest things in computer science are cache coherency, which is actually a really complicated problem, and naming things, which the joke is naming things we wouldn't think of as a hard thing, but it is. Okay. So double's a bad name. So this signature in ML is that signature in Java. This looks easy because you're used to it. This looks complicated because you're not used to it, but it does get, you do get used to it. But the thing about ML is you tend to do in ML, you're much more likely to just do essentially this and let ML figure out the signature. See, you're really likely to just do that and let ML figure out the signature. Okay. Now this is what Python looks like. But in Python, X doesn't have a type and Y doesn't have a type. So this function just takes in two things. And it just tries to do the best it can with, if you give it two strings, it'll try to convert a string to a real number, or it'll try to round a string. And you can get very strange things in a language like JavaScript or Python, because these things actually don't have types. So if your function just takes X plus Y, okay. If these are two ints, it adds the ints. If these are two doubles, it adds the doubles. If these are two strings, it concatenates them. If this is a string and an int, well, okay, it converts this int to a string and concatenates it to the string. So in a language like JavaScript and Python, the language just tries to make the most of whatever you give it. And if you give it two things where this doesn't make sense, you get a runtime error. If you end up giving it two things at runtime where the plus just does not make any sense, your program just crashes. The function's not wrong. It's just that if you call it with two things where the function doesn't know how to make sense of the plus, your program crashes, which is very bad feature of the JavaScript and Python languages. In our way of doing it, if you try to call this function with a string, ML will say, the compiler, before your program, the compiler won't compile it. You'll just get an error message from the compiler that says there's no way you can call this function with, you can't say f of 6g with cat here. Okay, that'll compile, that won't compile. In JavaScript, that'll compile, it may or may not run. In this case, it will run, but there are more complicated things where that'll compile and that'll compile, because it'll compile with any input here and any input here. It'll always compile, but it may not run correctly. It may crash your computer, or not, it may crash the program. So languages like JavaScript and Python, which don't have types for the variables, they just try to make the best they can out of whatever types they get at runtime. And if they can't make sense out of the function, then they blow up. Okay. If they can make sense out of the function, they do whatever they can. which is bad. That's considered, that's not considered a good strategy in the long run. Okay, now here's more examples. Okay, X, I'm going to take its product. Well, don't know what X is. This guy can be 2 ints or 2 doubles. Okay, defaults to 2 ints, so X is an int. Okay, here, don't know what X is. Still don't know what to do here. This could be 2 ints or 2 reals. Okay, but here it says, oh, the result of that guy is a real. Since the result of that guy is a real, that must have been the product of 2 reals, so this is a real number. Okay, go over here. Don't know what X is. This is either the product of 2 reals or the product of 2 ints. Don't know what this one is. Oh, but this one is a real. I think this, okay, I'm assuming that this binds this way. Okay, I'm going to assume that this one binds this way. So if X is a real, then this one must, then I know this is a real, so this is real times real. Okay, again over here, I don't know what X is. Product of 2 reals to 2 ints. Oh, but X is a real, so that feeds back over to here, X is a real. Okay, now look at G4. This one's different. This doesn't tell me anything. It could be 2 ints or 2 reals. This says that the return type is real. Okay, doesn't say what X is. It says that the return type is real. So the product of these two things is a real number. So that means that the input to them must be real numbers. So in fact, X is a real. But this was specifying the return type of the function, which specified the value that this product was a real. Okay, so the logic is, you read, the logic through this, the logic of reading this is different than the logic of reading that one or that one. Okay, this said the return type is real, so that meant that this product was real, so that meant that these inputs were real, so that means that this X is a real. Here, I tell you that X is a real, so product of 2 reals is a real. Okay, now I don't tell you what X is. Go over here. Not sure what to do here. This could be product of 2 ints or product of 2 reals. But then you say, but the result has to be the input to the real function. The input to the real function must be an int. This must be an int. So that means that this must be an int. So this is an int. So this takes in an int and gives me out a real. Okay. And then here, not sure what this is, but it's the input to the real function. So that means that X is an int. Okay, so X is an int. So X is an int. It goes into the real function. Product of 2 reals is a real. So this function takes in an int and gives me out a real. Okay, now let's go over here. Let's read this one. Don't know what X is. Well, X is the input to the real function. Okay, now why? I'm going to annotate this. This one actually doesn't work. There's a problem here. X is the input to real. So that means that X is int, because it must be the input to the real function. But the output of the real function is a real number. So that's the product of 2 reals. So that means that X is a real. Now I got conflicting information. Okay. Another way to put it is, if I look over here, this says that X is an int because it's the input to the real. This says X is a real because it's multiplied with the output of the real function. And I can't have X be both an int and a real at the same time. ML won't compile this. I have conflicting type information. Notice it looks pretty, doesn't look like bad code, but it is, because it subtly has conflicting type information. And then this one does the same problem. Okay, don't know what X is. Well, it's, that could be the product of 2 ints or the product of 2 reals. Not sure yet. Oh, but this is a real. So this means this is the product of a real number with a real number. So X must be real. But wait a minute, X is the input to the real function, so X must be int. So now I have conflicting information. I'm saying that X is real and saying that X is an int, so it won't compile. So it's conflicting type information. Okay, so practice reading these. So notice that I can deduce that this one won't compile and this one won't compile and this one will, these others will compile. Okay. All right. Now let's look at let's go through some more examples. we're practicing recognizing types and thinking about types. Okay, so what's this function do? Okay, takes in 4 things. What does it do with the 4 things? It adds the first 2. Oh, I'm sorry, it adds the first and the third. But what does that tell you? This is either 2 ints or 2 doubles. So this is either an int or a double, but since it doesn't know otherwise, it defaults to 2 ints. So that's an int and that's an int. Okay. Same thing over here. So these end up being 4 ints, and the return type is a pair of ints. So this function takes in 4 ints and gives us back a pair of ints. Okay. Now this one takes in 4 numbers, but see, this took in 4 numbers, which turned out to be ints. Here, from over here, we know that these are all ints. But this is 4 numbers, but this is 2 pairs of two numbers each. So F1 and F2 are not the same thing. Now, this is leading into what we're going to start talking about, pattern matching. This is a different pattern than that. It's what we're going to say, what we're going to see. F1 has one input pattern. F2 has a different input pattern. F1 takes in 4 ints. F2, its input pattern is 2 pairs of 2 ints each. Okay. F3 takes in 4 numbers. It's a different pattern. F3 is a pair of pairs of ints. Okay. This is a pattern we'll see, and it's a pair. So F3 takes F1 took in 4 things. F2 takes in 2 things. F3 takes in 1 thing. F4 took in 4 ints. F2 takes in 2 pairs. F3 takes in 1 pair, where each thing in the pair is a pair. Okay. F4 takes in 1 thing. What is it?
A tuple of 4.
A tuple, yeah, a quadruple or a 4 tuple. Yeah, there's no real, there's a bunch of different, it's a 4 tuple or a quadruple, but it's 1 thing. So F4 takes in 1 thing that is a 4 tuple. Okay, 4 ints, 2 pairs of, a pair of ints each. Okay, a tuple, a 4 tuple. I actually, here's another way I can get 4 numbers. So here's fun F5. I could take in what is F? Okay, and I always have the same right-hand side. Now, what is F5 taking in?
Is that a triple and an int?
Yeah, so it takes in 2 things. It takes in a triple and an int. Okay, it takes in 2 things, a triple and an int. Okay. Well, here's another. Here's another one. I'll do one more. Now you can do a lot of these. I'll make this one. Now what is this F6? What does he take in?
So it's a double consisting of a triple and an int.
Yeah, so it's 1 thing. It takes in a double, a pair. It takes in a pair, a tuple, a 2 tuple. Oh, notice how many words we have for 2 tuples. Some people call them pairs. Some people call them 2 tuples. Some people call them just tuples. A lot of times when people use the word tuple, they mean a 2 tuple. If they just say tuple, sometimes they mean a 2 tuple. Okay, so that thing takes in a 2 tuple, a pair, where the first thing in the tuple is a triple, and the second thing in the tuple is an int. Okay, okay, yeah, and I could keep building more of these. What's F7 take in?
A list?
A list, one thing, a list of 4 items specifically. In fact, we'll see that F7, if you gave it a list of 5 items, will complain. F7 takes in a list of 4 items. Okay, if you give it a list of 3 items, it'll complain. If you give it a list of 5 items, it'll complain. It specifically takes in a list of 4 items. Okay, now.
I have a question.
Yeah.
For I think F1, can X and U be ints and then Y and V be reals?
Yeah, sure, but I'd have to say that. Okay, since by default it gave me all ints, what do I do if I want those to be ints and those to be reals?
You would have to do the grouping, I think, on the left side.
Yeah, probably I would. Now, what does that do for me now?
So well, I don't think it'll compile because, well, V would have to be a real as well, right?
Yeah. Well, so what's it going to do? Will it compile?
As long as V is a real?
Well, no. See, you're misreading. You're thinking, what is the type of function F1 now? What does function F1 take in? What does ML conclude about it? What must it take in?
Do they all have to be reals?
No. Go through the logic.
Well, X is nothing or it's not defined, so it's just an int, right?
No. Don't use words like not defined. It's a parameter. What we're asking, what is the type? It's not specified here, but what does this tell you?
It's an int.
Pardon me?
It's an int.
Because plus takes 2 ints or 2 reals, since it's not specified here or here, it defaults to what? Plus takes 2 ints or 2 reals.
Since it's not specified, ML defaults to using ints instead of
Right.
reals.
Since it's not specified, don't use the word undefined. Because that's a loaded word. Undefined means something different. It's not specified or not declared. It's not declared, so ML infers it for you. It infers it using its rule. X plus is 2 ints or 2 doubles, 2 ints or 2 reals. If it's not specified, it defaults to 2 ints. Okay. Now, what about this plus? 2 ints or 2 reals. But what do I know now?
Y has to be a real.
Y is specified as real, so
V has to be a real.
Yeah, V is inferred to be real, and this compiles. And the input will be int real, int real. Int real, int real. That's a real good example. Yeah. So now I only need to say one of these, and then Python and then ML will infer the other one. Now do it again. Do it a different way. Get me the output being an int and a real, but write something else.
If just V, like if you did V : real.
Okay, that's pretty close to what we had a minute ago. I could just say that the V is real. Okay. And I think that groups like this, I think in that one, I don't even need the parentheses. I think it groups like that. Okay. That's another way to get the same thing, because now the V is specified as real. So that makes the Y real. Okay. Can you do it another way?
Couldn't you group the Y plus V on the right side?
Group them. They are, okay. Group them and do what?
I can't remember if it's : real as well or if it's something different.
Yeah. Now that's saying that the result of adding them should be a real. But if the result of adding them is a real, what does it tell you about Y and V?
That there would be ints.
Pardon me?
The parameters would be ints?
No, because if you add 2 ints, you get an int, and an int isn't a real. So if the result is a real, What does that tell me here?
They're both real.
They must be real because I either add two ints or add two reals. If I add two ints, I get an int. Okay. So then this would say that this is int, real, int, real. The two reals add up to give me a real. Okay. What if I drop that parentheses?
Is that just changing V?
Well, it does change V, but if V is real, plus has to take in what?
So Y has to be a
Reals.
real.
Right. So Y is inferred to be real. So this also affected Y because of the inference. If V is real, Y must also be real. So now I'm back to int, real, int, real. Okay. Now let me do a tricky one.
They're all ints.
They're all ints because no declaration of X and U. So you add, it defaults to adding two ints. No declaration of Y and V. Oh, but wait a minute. The input to real must be an integer. So actually, see, the input to real must be an integer. So the result of this must be an integer. So Y and V must be integers. But what does this function give me back? What's the output of this function?
A pair of an int and a real.
Yeah, a pair of an int and a real. See, instead of being the output being an int and an int, now the output is an int and a real. So now the function takes in four ints and gives me out a pair where the one pair is int and one pair is real. Now I could do that if, now here's an interesting question. That's the same thing as saying, remember how you specified the return type? You put a pair of parentheses around the last parameter and say colon. The return type now is int star real. Okay, int star real, a pair with an int and a real. Okay. Okay, this says that the return type of F1 is a pair of an int and a real. And that agrees with what I have over here. Can I now delete this thing? This one's a little bit tougher of a question. Let's infer what we can. X and U, no declaration. X plus U must be two ints or two reals. Okay, so that means that it defaults to two ints because I didn't declare here. And I did say that the output should be a pair of an int and a real. So that makes sense. This is an int. Okay, X is int, U is int, sum of ints give me int. Okay, let's move on. No declaration of Y and V. Y is not declared, V is not declared. So sum of two ints or sum of two reals, there's no information, so that's the sum of two ints. The sum of two ints gives you an int. This needs to be a real. This won't compile. Now, if this was Java, what would happen?
Java would let it happen because in Java, ints and reals are compatible so long as the output is expressed in a real.
Yeah.
Although even if it's not, it'll express it in an int with it rounded down or up depending on rounding.
So what we said, what does Java do? this thing's an int, the return type is a real, so Java does what? We've got a word for it.
It casts it to a real.
The actual word is usually promoted. Yeah, it casts or promotes it to a real. Okay, but it does it automatically. So in Java, it would look like this: double f int x int y return x plus y. Okay, we mentioned this. That is an int because x is an int, y is an int. That compiles to integer plus integer, gives you integer. And then it's magically cast or promoted to double for you automatically. Okay, if I wanted to be real fancy, I could write double here and do the cast myself, but Java will do it for me. Okay, Java will automatically do that cast or that promotion for me. ML will not automatically promote anything. So when this thing adds up to an int, but the result's supposed to be real, you get a compiler error. It will not promote it to a real. Okay, so that's why I really do need the real function call there. Okay, so this real does not force this thing to return a real like it does in Java. This double forces this thing to return a double as long as it's a legitimate cast. Java will automatically promote that guy to double. It won't go the other way. Now, Java is not completely idiotic about this stuff. What does this do? Double plus double gives me what?
Double.
Double. I want an int. So what does Java do now?
Demotes it, I would guess would be the term. Instead of promoting it, it would be demoting it to a.
It does not. It refuses to demote. It's ML-like in that case. What will this do in Java? This guy will
Give an error.
In
not
that case,
compile.
probably not compile. Yeah.
It won't, because Java won't do the demotion. Now I can do the demotion. I'm perfectly allowed to say I don't care about my decimal places; they can go away. I can do the downward cast. Yeah, you said it's actually called a downward cast or a narrowing cast. We have a whole bunch of different words for this. This one, the other one is called a promotion or an upward cast. Going from int to double is called a promotion or an upward cast. Going from double to int is called a downward cast or a narrowing cast. There's two kinds of casts. There is upward, which is synonymous with widening, which is sometimes called upwards. And then the other kind of cast, the words are, it's downward, a narrowing, or, I wrote upwards twice. It's upwards, widening, promotion. Okay, so downward, narrowing. I've never seen anybody use the word demotion. This cast going from casting it into a double is called upward, widening, or promotion. Casting a double to an int is called downward or narrowing. I've never seen it called demotion. Okay. So right now, let me type that more carefully. Okay, the one that went double, int, and returned. Well, you don't need the cast in this case. That one is upward, widening, promotion. Okay, this other one, which is going where you have to force the cast, that's called downward or narrowing. Okay, that one's called downward or narrowing. Okay, Java requires you to specify the downward cast. It'll do the upwards cast by itself. Actually, widening and narrowing are actually the terms that are used most often. This one is a widening cast. This one is a narrow. You know why it's called widening and narrowing? This one's widening. This one's narrowing. Think real hard. Those words have a real specific meaning. It's come out of the architecture class. Int is being converted to double. Why would I call that widening?
Because your doubles take more space.
But in what sense? Be real
More
precise.
bits.
More bits. What from what to what? Int is what?
Isn't it
32 bits.
32?
Double is
64.
64 bits. It's a wider word. It's a wider data type. You're going from a narrower data type to a wider data type. So it's called widening. This one's called narrowing because you're going from a wider data type to a narrower data type. Now, what's the problem? Why is this one automatic and this one not automatic? These are not trivial questions. These are profound. You really should know this stuff. You'll get asked, people will quiz you on this, like in job interviews. What's the point? Why is this one automatic and this one not? What is the widening and narrowing? What's going on? What's wrong with this?
It's allocating memory, and it's easier to deallocate than allocate.
No, that's not the problem. The compiler
Okay.
knows ahead of time. It's not allocating and deallocating. The compiler knows exactly what these things are ahead of time. These are actually not allocated and deallocated. They're local variables. No, that's not the issue. How did I get 3.14 to 3?
You round.
Yeah, but why is this okay and this is not okay?
Because you lose data when you downcast.
You're throwing away information. The rule of thumb is you never automatically throw away information. The compiler will never automatically throw away information. There is no, when you go the other way, notice there's no information being added. When you go from 3, when you go upwards, there's no information being added. So it's free. Now it is widening the data type, but it's not adding any information. When you go this way, not only are you narrowing, the real issue is you're throwing away information. The really important issue is you're throwing away information. Now let me show you why that's the real key to here. This is okay. This is still widening, but notice that this is a 32-bit value and this is a 32-bit value. It's called widening, but there is no widening of the data type. You're going from one 32-bit data type to another 32-bit data type, but you're still going from 32-bit int to 32-bit float, and there's no information being added. So but it's still considered widening, okay? Because and this is why these words are kind of weirdly ambiguous. This one's called widening when you go from int to float, but there is no widening of the data because it goes from 32 bits to 32 bits. But it's free. You go from 3 to 3.0. You're not adding any information. So that one's considered still widening. It's still considered an upward or a promotion. And this one really is widening. you're going from a 32-bit data type to a 64-bit data type. So you're very much widening the data type, but you're not adding, what the key is, you're not adding any information. This one is downward. This one is throwing away information. If I made these, floats, again, that's still downward, even though I'm going from 32 bits to 32 bits. But I'm going 32 bits, I'm still throwing away the decimal place. Yeah. So this, so we use the words widening and narrowing kind of vaguely here. It's motivated by going from int to double. Going from int to double is going from 32 bits to 64 bits. That's widening. But going from int to float is also called widening, even though they're both 32 bits. Okay. So going from int to double or going from int to float. Oh, let's see. Yeah, going from double to int is narrowing, but that's going from 64 bits to 32 bits. Going from double to int is narrowing, but that's going from 32 bits to 32 bits. So yeah, you can quibble that it shouldn't be called narrowing, but it is. Okay. Here, you're going from 32 bits to 64 bits. That's certainly widening. Here, you're going from 32 bits to 32 bits. It's hardly widening, but it still is called widening. Okay. Java won't do the narrowing either, and ML won't do the widening. Okay, so what's the difference between Java and ML? Neither one will do a narrowing cast. ML won't even do a widening cast, and Java will. And that's changing. Most modern languages like Rust won't do widening casts either automatically. People have decided that even the widening casts are a mistake. They shouldn't be done automatically. This is not such a great idea. Okay, it might seem convenient, but it's been determined over many years of debugging big software systems that it's been realized that automatic upward widening casts are really not a good idea. The ML people were right. They never allowed it from the beginning, and the Java people allowed it, and now they can't change it. It's too late. But now, like when the Rust language was invented, it was invented without widening casts. You do not get promotions from int to real for free. You got to do like ML. You have to say, convert it from an int to a real. You have to do the upward cast automatic yourself. You don't get upward cast for free, and you never get downward cast for free. All languages let you do these by calling functions. Java will do some of them for you for free. ML makes you call functions for all of them. Okay. So these are real good examples. Notice that by doing another language, we kind of force ourselves to think about the languages we thought we knew. Yeah, and this is how people actually really learn languages well, is by forcing themselves to learn another language, which makes them think harder about the language that they think they know. It's even true for foreign languages. If you learn another language, you'll probably end up speaking English better. As you learn more languages, you start realizing more about language in general. So that's true with programming languages, and it's true with human languages too. Okay, so it's good to learn another language, to even if it forces you to think more about the language you know, to appreciate these differences. That Java chooses to give you one kind of cast for free, but makes you force the other kind of cast. And ML doesn't give you any cast for free. Okay. Now let's switch gears a little bit and let's start talking about patterns. These actually are patterns. Okay. So I want to show you what I mean by patterns. Patterns are something that ML invented that are now considered, it's there were two things in ML that ML invented that are now becoming mainstream. One is type inference. That what we've been doing where we figure out what the variables are. The idea that I didn't tell you what X, Y, and Z are, I infer them. Okay, ML invented that. Now, for example, if you Google Java type inference, you'll find lots of, well, I didn't, okay. You'll find lots of information about type inference in Java. It's part of Java now, okay? If you Google C++ type inference, it's now part of C++. It wasn't there originally. It got added to C++. It came from the ML language. It's now part of C++. It's now part of Java. It's not as crucial to Java as it is to ML. It's not at the heart of Java, but it's been added to Java. Same with C++. It's been added to it. Okay. Now another example is pattern matching. So you can say Java pattern matching. Java pattern matching is interesting. Now you got to be careful. Java pattern matching, I do not mean regular expressions. Okay, this is what I mean. Pattern matching for Java. Notice that this is actually still in the process of being added to Java. Java does not yet quite have pattern matching. It's being added to the language. Okay, they think it's such a great idea that they're in the process now of adding it to the language. And it's something called Project Amber. So if you do Java, there's this thing called Project Amber, which is adding a bunch of new features to the Java language, and pattern matching is one of them. And type inference is part of it too. See, local variable type inference. So these are moving from the world of ML to the world of Java and C++. Similarly, C++ is in the process of adding these things. Okay. Now, JavaScript does not have type inference because it doesn't have types. But JavaScript has pattern matching, but they don't call it pattern matching. In JavaScript, it's called destructuring. This is something that was not in Java. See, did I spell it right? Oh. This was not originally in JavaScript. It was added in the 6th version of JavaScript. So it was added in what we call ES6, the 6th version of JavaScript. They added destructuring, which is their word for pattern matching. And I'll show you in a minute why they call it destructuring. Okay, so they use the word destructuring to mean this pattern matching. Okay, so these ideas from ML they're just moving and moving and moving out of the world of ML into the world of the more people are not going to be programming in ML. People don't like ML, but the ideas in ML are proliferating all over the place. And actually, I think over time people will get to realize that languages like ML really are a good language. I wouldn't be surprised if 20 years from now things look a lot less like JavaScript and Java and look a lot more like ML. I have a feeling that's my prediction for 20 or 30 years from now. But yeah, definitely the ideas of ML are moving into these languages. Okay, now let me start up the ML interpreter. Let me give you a couple of examples. Val x equals 1, 2. That's a tuple, right? So x is that tuple. Okay. And I can say val y is, say, cat 5 dog. Y is this triple. Okay. Notice it's a string int string triple. X is a int pair int times int pair. Okay. Now let me do kind of a funny thing. Notice that this was one variable representing one thing. Val, now watch this. I say u comma v equal 1 comma 2. I'm doing something you cannot do in Java, or you've never seen anything like this. I'm actually saying that notice here I said X is the pair 1, 2. So X represents that whole pair. Here I'm saying that this pattern should match this value. And if they match, make U that part of the value and V that part of the value. So what I'm doing is I'm declaring two variables out of a pattern. See, I actually declared two variables. Okay, X is the pair 1, 2. This is a pattern match. This is a pattern. This is a value. I matched the pattern to the value, and that declared the variables in the pattern. Okay, here's another example. Value a comma 4 equal 3 comma 4. This is a pattern that should match that value. The 4 matches the 4, and then that creates the variable a that matches the 3. So I'm declaring one variable now. Whoops, what did I do wrong? Oh, I get a little bit of a warning because, yeah, it did match the A. I also get we'll see later what these warnings are. But notice I did get the A. A is 3. So this patterns go on the left of equal signs. Now, here's the thing that's funny. You're used to thinking that a variable goes on the left of an equal sign. In Java, you write things like int x equal something. You always put a variable on the left of an equal sign. So you say int x equals 7. String y equals cat. Double z equals 3.4. Okay. Variable equals value. In ML, it's not variable equals value. In ML, you write val pattern equal value. Okay. The pattern can have variables in it. The pattern's supposed to match the value, and the variables in the pattern are matched up with things in the value. Okay. So this is ML's way of doing things. The assignment statement actually takes what we call a pattern on the left. If you put a single variable on the left, it matches any value. So we say that a variable matches any value. So if I say something like val y equal, the list 1, 2, 3, well, y is a variable, it'll match any pattern. Okay. But if I say something like val x, y, z equal 4, 5, 6, now I'm saying that that pattern should match that value. And if the pattern and the value match, then that is put in X, that is put in Y, and that is put in Z. Okay. Now I can screw up. That pattern doesn't match. There's more things over here than there are over here, and this thing will not work. It will not set any variables. The patterns didn't match. When you do this in ML, you got to make sure that the pattern does really match the value. Then the variables in the pattern get values assigned to them. Okay. Now, another way I could screw this up would be to not have enough variables over here. See, that won't match. Here's the thing that's interesting. Does that match? Do I have a value, a 5, and a value? This will match, and let X be 4 and Y be 6. See, X is 4 and Y is 6. Okay. If I do that one over again, and I put a 7 here. 5 doesn't match 7, so I don't this one won't work. Okay, it did not match anything because the pattern on the left didn't match the value on the right because the 5 didn't match 7. Values match themselves. Variables will match anything. One last thing before we leave. Okay. Oh, no, that's not going to work. Well, okay. Oops. On the left, I'm saying I need a list of 3 things. I'm saying I need a list of 3 things. So on the right, I should have a list of 3 things. The middle thing in this list is 7 dog. That matches 7 dog. So that means this X matches that whole first thing. See, a variable will match anything. This thing, I'm saying I want 1, 2, 3 things in a list. There's 1, 2, 3 things in a list. So X matches that whole thing there. Now, oh, and I'll do something a little bit trickier here. I'll make this one. Oops. Y comma Z. Real quick, anybody see what's X match? That whole thing there. This matches itself. What's Y?
6.
6, because this pair matches that pair, and the Z is the string 7. Oh. Okay. X got 4 cat, Y got 6, Z got pair. So the value declaration takes a pattern on the left and a value on the right. The pattern can be a mixture of variables and values, and then it declares the variables if they match the value appropriate, they match values over on the right. Okay. Oh, do you see why JavaScript calls this destructuring? You're essentially destructuring this value into its parts. So what you're really saying is that let X be that part of the value, let Y be that part of the value, let Z be that part of the value. And I think actually destructuring is a really good name for this. Pattern matching is not a bad name for it, and destructuring is not a bad name for it. The pattern destructures the value into its parts. Okay. Okay. And so that's the key idea, that a pattern destructures a value into its parts. And we're going to see how we can make use of this in function definitions in a really elegant way. You rarely do, what I'm doing here is not what ML does. This is just to demonstrate what I mean by patterns. Okay, this is not the way people use ML. The use of patterns comes up when you define functions, but it's easier to explain what a pattern is this way. So this is kind of a baby use of patterns as a way to explain what patterns are, and then we'll see how you really use them as a tool for defining functions. And the result is a very elegant structure. It's what makes people really impressed with the ML language, why people are adopting these ideas. So you end up with something that's very, what we say, expressive. You end up with something that's really It gives you a very nice way to describe functions. So we'll do more examples of this simple kind of pattern. Val pattern equals value. We'll do more examples of that, and then we'll see how we use that in defining functions. Okay, so we'll quit there because we're out of time. And if anybody has any questions, send me an email. I will see. Actually, I need. Oh, there's going to be a. Oh no, your next homework assignment is due on Tuesday, right? So you've got a programming assignment due on Tuesday. Yeah. So if you have questions about the program assignment, send me an email or come to office hours. So if there's any questions about the stuff in here, send email or come to office hours. All right. So I'll go ahead and quit there. Have a nice weekend and see you on Tuesday. Bye.